Hi, welcome to this video on halogenoalkanes. So halogenoalkanes are compounds in which one or more of the hydrogen atoms in the alkane have been replaced by a halogen atom, and a halogen atom is fluorine, chlorine, bromine, or iodine. The general formula is CnH2n plus 1x. X represents the halogen atom. So here are some examples of halogenoalkanes. Iodoethane, 2-chloropropane, and 1-bromo-2-methylpropane. So let's look at the different types of halogenoalkanes, and the type depends on how the halogen atom is positioned on the chain of carbon atoms. And this is important because there are some chemical differences between the various types. So here we have a primary halogenoalkane, and it's primary because the halogen group is attached to the carbon, which is only carrying one methyl group, therefore it's primary. A secondary halogenoalkane is when the halogen atom is attached to a carbon which is also carrying two alkyl groups, so in this case two methyl groups. And a tertiary halogenoalkane is when the carbon which carries the halogen is attached to three alkyl groups, in this case three methyl groups. So let's look at some examples of primary, secondary, and tertiary halogenoalkanes. When a hydrogen is replaced by a halogen, we use the prefix of fluoro for fluorine, chloro for chlorine, bromo for bromine, iodo for iodine. So again, these are primary, secondary, and tertiary. So an example of a primary halogenoalkane would be 1-chloroethane, because the chlorine is attached to a carbon which only has one methyl group, therefore it's primary. A secondary example would be 2-bromopropane, where the bromine is attached to a carbon which is attached to two methyl groups. And a tertiary is when the iodine in this example is attached to a carbon which has three methyl groups, so it's a tertiary. Here are some examples of skeletal drawings of halogenoalkanes. For example, here we have 1-iodopentane. So in order to name this, we first count the long chain of carbons. We have 1, 2, 3, 4, 5 carbons here, and the iodine is attached onto the first carbon. We also have 2-bromopentane, because there are 5 carbon atoms in the chain, and the bromine is attached onto the second carbon here. 3-chloropentane, again we have 5 carbon chain, and the chlorine is attached onto the third carbon, so 1, 2, 3. And also 1, 2, 3 from this end as well.
So let's now look at the physical properties of halogenoalkanes. So the chart here shows the boiling points of some simple halogenoalkanes. The green line represents room temperature, the red bars are chlorides, blue bars are bromides, and yellow bars are iodides. So notice that there are three, this one, and this one, which have a boiling point below room temperature. So these will be gases at room temperature: chloromethane, bromomethane, and this is chloroethane. So all these three will be gases. And chloroethane is also a gas, which is this red one here. And the pattern in boiling point reflects the pattern in intermolecular attractions. So we have van der Waals dispersion forces, and these attractions get stronger as the molecule gets longer. Therefore, there are more electrons. So this increases the size of the temporary dipoles that are set up, and this is why the boiling points increase as the number of carbon atoms in the chain increases. So let's look, for example, at the red bars of the chloride as an example. Dispersion forces get stronger as we go from 1 carbon in the chain to 2 carbon in the chain to 3 carbon in the chain. So it takes more energy to overcome them, and so the boiling points rise, which we can see here. Also, we need to be aware of the fact that the carbon-halogen bond, apart from the carbon-iodine bonds, are very polar, because the electron pair is pulled closer to the halogen atom than the carbon, and this is because the halogens are more electronegative than carbon. So here we have the electronegativity values. Carbon is 2.5. We can see that fluorine is 4, therefore it's more electronegative. Chlorine 3, also more electronegative. Bromine also more electronegative than carbon, but iodine is the same, therefore the carbon-iodine bond is not polar. So, and this electronegativity means that in addition to the dispersion forces, there will be forces due to the attraction between the permanent dipoles, and again, except the carbon iodide. And the size of those dipole-to-dipole interactions will fall as the bonds get less polar. So as you go from chlorine to bromine to iodide, for example. Nevertheless, the boiling points rise. This shows that the effect of the permanent dipole attractions is much less important than that of the temporary dipoles, which cause the dispersion forces. Therefore, the large increase in number of electrons by the time you get to iodide completely outweighs the loss of any permanent dipoles in the molecule. Let's now consider the boiling point of isomers. And the examples shown here, we can see that the boiling point falls as the isomers go from primary to secondary to tertiary halogenoalkane. And this is simply as a result of the fall in the effectiveness of the dispersion forces. And the temporary dipoles are greatest for the longest molecule, and the attractions are also stronger if the molecule can lie closely together. Therefore, the tertiary halogenoalkane is as we can see, it's very short and it's quite fat. Therefore, it won't have much close contact with its neighbors. Therefore, it's got a lower boiling point.
Let's now consider the solubility of halogenoalkanes in water and also other organic solvents. So generally, halogenoalkanes are only very slightly soluble in water. So in order to dissolve a halogenoalkane, you will need to first break the attraction, in this case van der Waals and dipole-to-dipole interactions between the halogenoalkane molecules. And also, we also have to break the hydrogen bonds between the water molecules. So both of these require energy, but energy is also released when new bonds form. And because in this case we only have dispersion forces in dipole-to-dipole interactions and they're not hydrogen bonds, which means that the new bonds are not as strong. So generally this is not energetically favorable. However, halogenoalkanes tend to dissolve in organic solvents such as ethanol because new intermolecular attractions have the same strength as the broken bonds.
Let's consider chemical reactivity of halogenoalkanes. So here is a pattern in the strength of the 4 carbon halogen bonds. We have the carbon fluorine, carbon chlorine, carbon bromine and carbon iodine bonds. And first of all, for a reaction to happen, we first need to break the carbon halogen bond. So it's easier as you go from fluorine to chlorine, from fluoride to chloride to bromide to iodide, as represented here, as the compounds get more reactive in that order. So iodoalkanes are the most reactive and fluoroalkanes are the least. And this is shown by this pattern here. Also, of the 4 halogens, fluorine is the most electronegative and iodine is the least. That means that the electron pair in the carbon fluorine bond will be dragged mostly towards the halogen end. So if we look here, we have some methyl halides, and we can see with the fluorine to carbon bond that the carbon becomes quite delta positive and the fluorine quite delta negative. And as we go down to iodine and carbon, there's no polarity because these have equal electronegativities. And bond polarities in general are important in relation to halogenoalkanes because they undergo a set of reactions where the halogen is replaced by something else, and these are called substitution reactions. We will cover these later on when we discuss nucleophilic substitution reactions.
So let's look at preparation of halogenoalkanes. So let's first consider bromoalkanes and iodoalkanes. So to make bromoalkanes, we would need to treat the alcohol with a mixture of either NaBr or KBr and 50% H2SO4, and this will give us HBr, which will then react. We do not use concentrated H2SO4 because most of the HBr will initially produced will be oxidized to bromine by the concentrated acid. So here we have the example of what happens when we have an alcohol reacting with HBr to produce a halogenoalkane, and a molecule of water. So we warm the mixture of the bromoalkane, and the boiling temperature is about 59 degrees centigrade, and that of alcohol is 82 degrees centigrade. Because the boiling temperature of and bromoalkane is lower, it will distill off and is condensed and collected. So how do we make iodoalkanes? Well, again, we react an alcohol with a mixture of Na or K iodide and concentrated phosphoric acid, which will produce hydrogen iodide, which then will react with the alcohol to form an iodoalkane. So this is the equation here. Here we have ethanol reacting with hydrogen iodide to produce iodoethane and water. There is another method. We can warm the alcohol with a mixture of damp red phosphorus and iodine. The iodine will react with the phosphorus to produce phosphorus triiodide, which will then react with the alcohol. A note here at the bottom, remember that phosphoric acid, and we use phosphoric acid instead of sulfuric acid because sulfuric acid will oxidize the iodide ions and hardly any hydrogen iodide will be produced, and this is similar for bromine.
Preparation of halogenoalkanes, in this case chloroalkanes. So halogenoalkanes can be made from the reaction between alkenes and a hydrogen halide, but more commonly we use a reaction where we replace the OH group in the alcohol by a halogen atom. So this is the general formula. We have an alcohol reacting with a hydrogen halide to produce the RX with water. So how do we make chloroalkanes? Well, the simplest method is to use phosphorus pentachloride with the alcohol. So for example, if you wanted to make 2-chloropropane, we would add BCl5 to propantool. To make a tertiary halogenoalkane, we shake the corresponding alcohol with concentrated hydrochloric acid at room temperature. So here is the example. We have the tertiary alcohol reacting with HCl. In this case, the OH group is kicked off and the Cl attaches to the carbon to produce the tertiary halogenoalkane, and we also get water. We can also use sulfuric acid with the mixture of propantool and KCl, but this method is generally less efficient because dehydration of the alcohol to propene also takes place at the same time. So let's look at the reactions between halogenoalkanes and hydroxide ions, and the hydroxide ions can either come from sodium or potassium hydroxide, and we will cover both substitution and elimination reactions. There are two different sorts of reactions that you can get, but this depends on the condition used and the type of halogenoalkane. And primary, secondary, and tertiary halogenoalkanes behave differently in this respect. So let's first consider the substitution reaction. So a substitution reaction is when an atom or a group of atoms is replaced by another atom or group of atoms, and you will always have two reactants and two products. And in this, with halogenoalkanes, the halogen atom is usually replaced by an OH group to give an alcohol. This is also referred to as nucleophilic substitution, where the attacking group is a nucleophile. Just a reminder, a nucleophile is a species with a lone pair of electrons that is used to form a covalent bond with the delta positive atom in another molecule. And the nucleophile will attach to the delta positive carbon atom in the halogenoalkane. So in the substitution reaction, the halogen atom is replaced by an OH group to give an alcohol. So here we have an example to produce where in this case the Br has been replaced to the OH. So we're going from a bromoalkane to an alcohol. And this is the ionic equation for the above. So in the example, 2-bromopropane is converted into propan-2-ol. The halogenoalkane is heated under reflux with a solution of sodium or potassium hydroxide. Heating under reflux means heating with a condenser placed vertically in the flask to prevent loss of volatile substances from the mixture. The solvent is usually a 50-50 mixture of ethanol and water, and we do this because everything will dissolve in that. So the halogenoalkane is insoluble in water. However, if you use the water alone as a solvent, the halogenoalkane and the sodium hydroxide solution wouldn't mix, and the reaction could only happen where the two layers met. Therefore, 50-50 with ethanol and water will make sure that everything dissolves. So let's consider the elimination reaction. So halogenoalkanes also undergo elimination reactions in the presence of sodium or potassium hydroxide. So in this case, we have 2-bromopropane will react with NaOH to give us an alkene, in this case propene. Notice that a hydrogen atom has been removed from one of the end carbon atoms together with the bromine from the center one. In all simple elimination reactions, the things being removed are on adjacent carbon atoms, and a double bond is set up between those carbons. So in this case, the bromine is attached to the central carbon, and this hydrogen is adjacent to the carbon where the bromine is attached. And this is represented here to show that the double bond will form between those two carbons, because we're losing the hydrogen from here and the bromine originally from here. And then again, in this case, the halogenoalkane is heated under reflux with a concentrated solution of sodium or potassium hydroxide in ethanol, and then propene is formed, and because this is a gas, it passes through the condenser and can be collected. So now that we've considered both types of reactions, what decides whether you get substitution or elimination? Well, the reagents you are using are the same for both substitution and elimination. So you will have the halogenoalkane and either sodium or potassium hydroxide solution. In all cases, you will get a mixture of both reactions happening. So some substitution and some elimination. What you get most of depends on the number of factors. So let's consider there are 4 different factors that influence this. So first of all, the most important one is what halogenoalkane you're using. So for example, whatever you do with the tertiary halogenoalkanes, you will tend to get mainly the elimination reaction, whereas with primary ones, you will tend to get more substitution. However, you can influence things to some extent by changing the conditions. So again, this summarizes it. So if you have a primary halogenoalkane, you're more likely to get mainly substitution, secondary a mix of both, and for tertiary mainly elimination. But you can also alter the solvent, the temperature and the concentration, which we'll discuss now. So for the solvent, the proportion of water to ethanol in the solvent matters. So water encourages substitution, whereas ethanol encourages elimination. With temperature, the higher the temperature you use, the more elimination reactions you will get. With concentration of sodium or potassium hydroxide, the higher concentration favors elimination. So let's just do a quick overview. So in summary, for a given halogenoalkane, to favor elimination, we would use a higher temperature, a concentrated solution of sodium or potassium hydroxide, and pure ethanol as a solvent. And in order to favor substitution, we use lower temperatures, more dilute solutions of sodium or potassium hydroxide, and more water in the solvent mixture. So let's look at the reaction between the halogenoalkanes and ammonia. So the reaction details and products, we'll discuss this first. So halogenoalkane is heated with a concentrated solution of ammonia in ethanol. The reaction is carried out in a sealed tube. You couldn't heat the mixture under reflux because the ammonia would simply escape up the condenser as a gas. So let's consider the example of 1-bromoethane as a typical primary halogenoalkane. And there is no difference in the details of the reaction if we choose a secondary or tertiary halogenoalkane instead. We will get a series of amines forming together with their salts. and the reaction happen one after another. So let's first look at making a primary amine. So the reaction happens in 2 stages. In the first stage, a salt is formed. In this case, we've got ethyl ammonium bromide. This is just like ammonium bromide, except that one of the hydrogens in the ammonium ion is replaced by an ethyl group. So this is the reaction for this. And then there is a possibility of a reversible reaction between this salt and excess ammonia in the mixture, which is represented by this equation here. The ammonia removes a hydrogen ion from the ethylammonium ion to leave a primary amine, in this case ethylamine, and this is our primary amine here. So the more ammonia there is in the mixture, the more of the forward reaction is favored. So let's look at making a secondary amine. The reaction doesn't stop at the primary amine, so the ethylamine also reacts with the bromoethane in the same stages as before. So in the first stage you get a salt formed. This time we get ethylammonium bromide. Think of this as the ammonium bromide with 2 hydrogens replaced by the ethyl groups. So these are the ethyl groups. There is again the possibility of a reversible reaction between the salt and excess ammonia in the mixture, which is represented by this equation here. So the ammonia removes a hydrogen ion from the diethylammonium ion to leave a secondary amine, diethylamine. A secondary amine is one which has 2 alkyl groups attached to the nitrogen. So in this case we've got the nitrogen, we've got 1, 2, therefore it's a secondary amine. Let's look at making a tertiary amine. The diethylamine also reacts with bromoethane in the same 2 stages as before. So in the first stage we get triethylammonium bromide, represented here. There is again the possibility of the reversible reaction between the salt and excess ammonia in the mixture. The ammonia removes a hydrogen ion from the triethylammonium ion to leave the tertiary amine. And a tertiary amine is one which has 3 alkyl groups attached to the nitrogen, as shown here. So we have the nitrogen here, we have 1, 2, and 3 groups attached. And finally, we look at making a quaternary ammonium salt. So in this case, the triethylamine reacts with bromoethane to give a quaternary ammonium salt, and this is where all the 4 hydrogens have been replaced by alkyl groups, as shown here. So we have the nitrogen, we have 1, 2, 3, and 4. So and because we've replaced all the hydrogens and there are no more hydrogens left on the nitrogen to be removed, the reaction will stop here. Let's look at the reactions involving halogenoalkanes and silver nitrate solution. So we'll discuss how silver nitrate solution can be used as part of a test for halogenoalkanes and also as a means of measuring their relative reactivities. So how do we test for the halogenoalkane? Well, we use silver nitrate solution to find out which halogen is present in a suspected halogenoalkane. And the most effective way is to do a substitution reaction which turns the halogen into a halide ion, and then to test for that ion with silver nitrate solution. So first of all, we warm the halogenoalkane with some sodium hydroxide solution in a mixture of ethanol and water. Everything will dissolve in this mixture, and so you can get a good reaction. The halogen atom is displaced by a halide ion, as represented here, or hal for the halogen, plus the OH, or the hydroxy ion. We'll get ROH plus the halide ion. There is no need to make this reaction go to completion. The silver nitrate test is sensitive enough to detect fairly small concentrations of halide ions. So the next step would be to acidify the mixture by adding dilute nitric acid, and this will prevent any unreacted hydroxide ions reacting with the silver ions. And then we add the silver nitrate solution, and various precipitates may be formed from the reaction between the silver and the halide ions, as represented here. And depending on what we observe, we can then determine which halide ion is present. So if we have a white precipitate forming, it's most likely to be a chloride ion. If we have a very pale cream precipitate forming, it's most likely to be a bromide ion. And if it's very pale yellow, it's most likely to be an iodide ion. And then it's actually quite difficult to distinguish between these colors, especially if there isn't very much precipitate. So we can confirm the precipitates by adding an ammonia solution. And if we have AgCl forming, the precipitate will dissolve to give a colorless solution. And if we have AgBr forming, then the precipitate is almost unchanged if we use dilute ammonia, but dissolves in concentrated ammonia solution to give a colorless solution. And also AgI, the precipitate will be insoluble in ammonia solution of any concentration. So this is how we would then confirm the first observation that we made. Let's now consider the mechanism of nucleophilic substitution, and in this case we will look at the primary halogenoalkane reacting with ammonia, and this is also known as SN2. So in the first stage, the collision between two species is required, and this is the slow step. So here we have the ammonia and the primary halogenoalkane colliding. In the second stage, the ammonia molecule may remove one of the hydrogens on the NH3+. The ammonium ion is formed together with the primary amine. This reaction is reversible, so the products will be a mixture of ethylammonium ions, ammonia, ethylamine and ammonium ions. The major product will only be ethylamine if the ammonia is present in very large excess. So as we know from before, the reaction doesn't stop there. The ethylamine is a good nucleophile and goes on to attack the unused bromoethane. In this case, we have a tertiary halogenoalkane reacting with ammonia. So we heat the halogenoalkane in a sealed tube with a solution of ammonia in ethanol. And again, we have two stages. First of all, we have the initial ionization of the halogenoalkane. And this is known as an SN1 reaction. In this case, because we only have one species of halogenoalkane involved. And this is a slow step because we're basically waiting for the bromine to just fall off to produce the carbocation in the bromine ion. And the second step is the rapid attack by the ammonium on the carbocation to form this here. In the stage 3, the ammonia molecule removes a hydrogen ion from the NH3+ group in a reversible reaction, and the products are an ammonium ion and an ammonium ion and an amine. Let's quickly consider Grignard reagents. So the general formula is RMgX, where X is the halogen, the R is an alkyl group, and Mg obviously stands for magnesium. So how do we prepare this reagent? And we make these by adding halogenoalkanes to small bits of magnesium in a flask containing an ether. The flask is fitted with a reflux condenser, and the mixture is warmed over a bath for about 20 to 30 minutes. Just a warning, ether is very dangerous to work with and is an anesthetic and is extremely flammable, so don't do this unsupervised. So let's consider some uses of halogenoalkanes. So they're often used as chlorofluorocarbons, or CFCs for short. These are compounds that contain carbon with chlorine and fluorine atoms attached. They're non-flammable and not very toxic, and they were widely used in refrigerants, propellants of aerosols, and also for dry cleaning. So if they're not toxic and non-flammable, then why are we not using them? Well, the problem is that CFCs have a very devastating effect on the ozone layer. And the ozone layer, as we know, filters out harmful ultraviolet light, which can cause skin cancer. And for a while, CFCs were used in refrigeration and aerosol propellants. And the major problem is the stability of this molecule. And the concentration has slowly built up in the atmosphere. In the stratosphere, CFCs absorb UV light and form chlorine radicals. It is these chlorine radicals that break down the ozone to oxygen. So let's just quickly look at what ozone is. So ozone is 3 oxygen atoms joined together. We have low-level ozone in the troposphere, which causes respiratory problems, and the destruction of the high-level ozone allows harmful ultraviolet radiation to reach Earth. So ozone is very important because it filters out most of the harmful UV radiation. And before the ozone layer was formed, there was no life on Earth. UV radiation is divided into A, B, and C is the most harmful and is blocked out completely by ozone. A is the weakest, and only a small amount is absorbed by the ozone. And UV radiation A is the one that gives a tan and ages your skin prematurely. So what are the alternatives to CFCs? Well, we can use carbon compounds which contain hydrogen as well as halogen atoms. And these have shorter life in the atmosphere than CFCs, and much of them is destroyed in the low atmosphere, so it doesn't react with the ozone layer. We also have hydrofluorocarbons, which are HFCs, and these are compounds containing only hydrogen and fluoride attached to the carbon. Because these don't contain any chlorine, they have zero effect on the ozone layer. And these are widely used in refrigerants for blowing foam plastic and also as propellant in aerosols. And also hydrocarbons, these have no effect on the ozone layer, but they do have a downside. They are highly flammable and are involved in environmental problems such as the formation of the photochemical smog. Let's look at some other uses of halogeno compounds. Well, making plastics. So we're not strictly speaking about halogenoalkanes, but more it's more correct to say that we're dealing with halogenoalkenes. And these are used, as we discussed in a previous video, in chloroethene or tetrafluoroethene. So chloroethene also stands for PVC, can be used for windows and other things, and tetrafluoroethene is used for non-stick pans and so on. And halogenoalkanes also react with many compounds, so they're very useful in the lab as intermediates in making other organic chemicals.